Okay, good afternoon, and welcome to our Mitigating RPZ Backflow Discharge webinar. We're joined by Cameron Rappaport, our Backflow Product Specialist. During the duration of today's presentation, phone lines will be muted, but we encourage you to submit questions via the chat window. Just hover over the chat icon at the bottom of the WebEx and type in your question. We'll then address them after the presentation. So with that, let me pass it off to Cameron to get started.
All right, thank you for the introduction, Greg. Welcome, everybody. As Greg said, my name is Cameron Rappaport, and I am the Backflow Product Specialist here at Watts. What that means is that I do everything backflow here, from trainings such as this to trainings in person at one of our excellent training facilities to marketing to new product development. So if it has something to do with backflow, I usually have my hands on it in one way or another. So let's dive right into it. Let's talk about mitigating RPZ backflow discharge. Just one thing to note to make sure we have all the CEU stuff covered if you're here for ASPE CEUs. This course is approved for ASPE CEUs only, so it's not necessarily approved for the PE professional development hours. If you're certified in plumbing design or you're a certified plumbing design technician, you can use this course towards recertification. This may or may not be accepted for PE renewal, and you'll have to inquire with your state if you can get this to count towards it later. So that being said, let's move right along. So today's objective. So after this webinar is complete, you should be able to understand the operation of an RPZ backflow preventer. So understand some basic root cause analysis of a discharging RPZ backflow preventer, how to determine worst case discharge, understand the proper and the purpose of that installation of a strainer within RPZ backflow preventer, and understand the new flood mitigation devices now on the market, which is something I'm particularly excited to talk about. So I'm just going to real quickly go through some terms at the beginning to make sure we're all on the same page. For those of you who might be backflow professionals, I know this might be a review, so just bear with me. First things, cross connection. So in order for contaminants to get into a water distribution system as a result of backflow, which is the thing we're trying to prevent, you need three things: a cross connection, a source of contamination, and a backflow event. So let's break down that first thing, a cross connection. So as defined by the EPA, a cross connection is any actual or potential connection between a public water supply and a source of contamination or pollution. So these are a hazard to building occupants, and they can jeopardize the cleanliness and potability of our public water system. So what's the difference between an actual and potential connection? An actual connection is a direct connection to a source of contamination, like your boiler right here. The water in your boiler is considered non-potable, and you have a hard pipe right to it. And a potential connection is something like a hose. It's not necessarily connected to anything, but you can go and you can drop it in a pond, a bucket of pesticide, whatever you're going to use that hose for, and it'll create a cross connection. Backflow is the unwanted reverse flow of a liquid, gas, or other substance into the potable water distribution system. So our potable water distribution is built to operate in one direction. It goes from distribution to use. So when that direction reverses and you have cross connections downstream that are unprotected, that is how you introduce contaminants. So in this case, if the water main breaks, there's the potential to siphon any number of contaminants from all of these unprotected cross connections. So you have dirty water, if there's an unprotected sprayer submerged in the bath or sink, the stagnant water or glycol in the boiler, stagnant pools of water or fertilizer in your sprinkler system. There's lots and lots of these cross connections. Last couple terms, guys, before we get into the meat of this. Back siphonage. So back siphonage can occur when there is a negative or subatmospheric pressure at the supply side of a cross connection. So these conditions typically occur due to something like a water main break or extremely high demand from stuff like firefighting operations. This results in a partial vacuum being drawn on the non-potable system. So this will siphon pollutants or contaminants into the potable water system through an unprotected cross connection, like a hose bib or a hydronic system makeup connection. So you can think of back siphonage as a pull from the supply side. So this leads us to our next term, back pressure. So if back siphonage is a pull from the supply side, back pressure is a push from downstream side. This occurs when you have an elevated pressure downstream of a cross connection. So this could be caused by installation of pumps, which is going to increase pressures above your supply pressure, or something like thermal expansion, which can result in excessive pressure, which will act to move that potential contaminant in something like a boiler, great source of thermal expansion, into your potable water system. Basic terms, so these are common terms. I'll go through them quickly. I'm guessing you guys know them, but for the sake of completeness, I'll review them fast. Pressure, force per unit area. We're going to talk in PSI. For those of you who use metric, I'm sorry. We're giving this presentation from Massachusetts. There's also flow rate and velocity. Flow rate is the amount of fluid that goes through a pipe in a specific amount of time. We're going to use gallons per minute when we're talking today. All right, so our key elements of cross-connection control. We have isolation. That's point of use control. That's something like your backflow preventer at your hose bib, your backflow preventer at your hydronic system. Then we have containment. This is protecting the public water supply. This is the backflow prevention at the source, right where your water meter is. This is typically governed by your water purveyor as opposed to isolation, which is governed by local or national codes and ordinances. So total backflow protection is protection both at the meter and at the point of use. So where do these all get used? Well, they're extremely common. And every cross connection requires appropriate backflow connection. Here you can see they have backflow containment at all the service lines. They also have isolation protection at all these different points of use. They can go from anywhere in the building, from the basement up to the top floor. So let's talk about reduced pressure zone assemblies. These are marked in purple on this diagram. They're extremely common. You can see we have one down here. This would be your point of source, but they have one for the boiler, one all the way up at the top floor for an air conditioning unit, another at the point of source here. They're an extremely common type of backflow preventer. So let's get right into it, talk about what they are and how they work. So here are a bunch of pictures of different reduced pressure zone assemblies. They come in all sorts of materials, shapes, sizes. This is really going to be the focus of our presentation. So other than an air gap, which is nature's backflow preventer, you're using gravity on your side, this affords the highest possible degree of protection, which is why it's so ubiquitous. It's used for contamination or isolation, back pressure and back siphonage. It's rated for health hazard applications as well as continuous pressure. So if you know anything about backflow, these are checking all of the boxes. The downside is that it will occasionally discharge water due to an integrated differential pressure relief valve. And in catastrophic events, it can discharge a very, very large amount. It also must be installed a minimum of 12 inches above grade, and it typically cannot be installed vertically. There's also a testable backflow preventer. Notice that it has test cocks and shutoffs. A backflow preventer is approved only with a certain set of shutoffs, so it must remain at the inlet and outlet for it to be an approved assembly. So let's get into the inner workings of an RPZ type backflow preventer, because they are reasonably complicated. One thing I do want to touch on first, if you see reduced pressure detector assemblies, they work exactly the same way as a reduced pressure zone assemblies, but they have that low flow metered bypass. They're typically only used in fire protection. If you have any questions about our PDAs, feel free to give me a shout later, because they're largely out of scope of this presentation. So here you see a cross connection of an RPZ backflow preventer. Now, how do these work? Like many backflow preventers, the main safety mechanisms are check valves, also known as non-return valves. They allow water to flow in one direction only. As you can see here, we have one check valve that I'm circling with my pointer now, and a second check valve down here. So we have an upstream or supply pressure. Right here, it's 60 psi. A downstream pressure. Right here, it's 54 psi, excuse me. And we have the check pressure in between the two checks. This is often referred to as the zone. In fact, this is the reduced pressure zone. Here, this is 55 psi. We also have a relief valve down at the bottom. So let's go through all of these components to see how they all work together to make this one of the safest types of valves that you can get. So here's our first check. This is a minimum 5 psi check. What this means is that the spring is sized to only open when at minimum there is a 5 psi differential across the check. As you can see, this creates a pressure drop from the supply pressure of 60 psi to the zone pressure of 55 psi. I've been saying minimum because that 5 psi is what is required by code. Most of the time you're going to see this somewhere between 6 and 8 psi, but for our purposes, for the rest of this presentation, I'm just going to talk about those minimum acceptable values to keep everything easy. Here we have our second check. This is a 1 psi check. So that has that minimum differential pressure of 1 psi across it to open. You can see this with the 1 psi drop off between the zone pressure and the downstream pressure. Finally, we have one more spring, and this is the relief valve spring. This is a minimum 2 psi relief valve spring. This is biasing the relief valve open. Now, earlier I mentioned that this is a differential pressure relief valve. This is because its opening point is being driven by the differential pressure between the upstream or supply pressure, in this case 60 psi, and the zone pressure, 55 psi. So if you look down here, we have a diaphragm that's acting on this rod. On one side, you have supply pressure. And on the other side, you have the zone pressure, which is being helped by that 2 psi spring. So a little bit of math on this particular one. On one side is our zone pressure, plus 2 psi, which is 57 psi. That's trying to open it. The other side is the supply pressure. It's 60 psi. So this should stay closed because 60 is larger than 57. This is the basic function of this valve. So what happens when it's flowing? So previously, this slide, static, no flow. You can see those checks are closed. What happens during flow? When water is flowing through the valve, the pressure drop across the checks should be higher than their minimums. This is because if a check opens at 5 psi, to open it more to get more flow, you require a higher pressure differential to drive that check open further. This is an important concept which will come up later. So here's a nice animation cutaway so we can see what's going on. As you can see, first the water is going to close that check, right? It only takes 2 psi. Then 5 psi will open the first check, fill the zone, open the second check, and now we have flow. So our relief valve is staying closed because nothing's going wrong. So under normal operation, this relief valve is going to stay closed. So what happens when something goes wrong? In this case, a fouled first check. So debris gets stuck in that first check when water is flowing. When the flow stops or is reduced, that check is now stuck open. This will make it so the supply pressure will migrate past the first check, raise the pressure downstream. Now when the pressure between the two checks gets within that 2 psi of supply pressure, with the help of the relief valve spring, the relief valve is going to open. You have water on your floor. We're going to go into this with a little bit more detail later. So the size of the debris will dictate the size of the leak. A grain of sand or some pipe tape might cause a slow drip. A large rock could cause a high flow continuous stream. This serves two purposes. If indeed there is a backflow event occurring, the potentially contaminated water will go on the floor or the ground instead of back into the potable water system. This is what gives the valve such a high degree of safety. It puts the water on the floor instead of into your drinking water. This also gives a visual indication of failure. So unlike a double check, which is another common testable backflow preventer, but a double check doesn't have a relief valve, you only know it's working when you test it. Usually an annual test, 364 days a year, you have no idea if it's operating correctly. An RPZ tells you if something is wrong. So let's look at something that's not moving to make this a little bit easier to see. So here's a static picture of a valve. The flow has stopped, and you have some debris holding that first check open. This has allowed the supply pressure to increase the pressure of the zone above the typical 5 psi drop. So if this was operating correctly, that zone pressure should be 55, not 58. Once that pressure raises up and it gets within 2 psi of opening pressure, now we have 58 psi plus 2 psi of the spring is 60. Right? It's going to match the supply pressure. Now any more pressure migrating across that is going to open the relief valve, and you get water on your floor. The relief valve will flow as much as it needs to in order to ensure that that minimum 2 psi differential is met. So anywhere from a slow drip on that grain of sand stuck against your check seat to a torrential downpour in case of something catastrophic happening. Now what about a fouled second check? This is much less common than a fouled first check, but it can happen. This can also cause the relief valve to open, but only if there is back pressure in the system. Otherwise, there's no way to raise the pressure in the zone between the two checks to open the relief valve. So again, let's take a look at something that's not moving, make this a little bit easier to understand. So here we have a fouled second check. You can see the debris is holding check number 2 open right there. And we have back pressure. Something in the system is creating additional pressure. It's 100 psi. This situation is a reasonably hazardous one, as the pressure of the potentially contaminated water is threatening to overwhelm the pressure of the potable supply, and all that's stopping it is one check valve. Or it would only be one check valve if it weren't for the differential pressure relief valve. That's doing its job, and it's going to discharge the contaminated water to drain. So to make it more clear, you have 100 psi here. This is going to raise the pressure in the zone through that fouled second check. Once it gets within 2 psi of the supply pressure, that spring is going to help it, and it's going to open that relief valve. And again, that contaminated water goes on the floor to the drain instead of into your drinking water supply. So here's our worst case scenario. Right. Back siphonage, back pressure, 2 fouled checks. So without the relief valve, this would just be another piece of pipe. And that back siphonage would suck all of these contaminants right into the water supply. But because of the relief valve, the potable water supply remains safe. So here you can see with 0 psi, so with no supply, right? So 0 or subatmospheric, right? Could be negative. The relief valve is always going to be open because it has no pressure there sitting on that side of the diaphragm to force it closed. So in this situation, it will remain open as long as the supply pressure is below 2 psi. One of the reasons that the discharge rate of these valves can be so high is because they are designed for exactly this worst case scenario. So you have 2 fouled checks, you lose pressure, right? You have a water main break. We want to make sure that this valve is going to keep our water safe. So it has to discharge quite a bit to do that. Last thing I would like to note on the operation of an RPZ backflow preventer is how supply pressure fluctuations in water hammer can affect the valve. So, supply pressure fluctuations. If you're towards the end of a distribution leg or you're near some sort of large intermittent uses of water, maybe hydrants are being flushed, these are all reasons that supply pressure might drop or not be consistent. So your relief valve, say it drops down to 57 psi from 60, your relief valve doesn't know the difference between rising pressure in the zone versus falling pressure on the inlet. So when that water pressure on the supply side gets within 2 psi of the zone, that relief valve opens. So this is one reason that you see what we call spitting. Your water pressure is going all over the place. It falls. The valve's going to open briefly. It's going to release a little bit of water. Then it's going to drop that pressure in the zone. It's going to close again. You can also have water hammer. Water hammer is a pressure surge that occurs as a result of a fluid changing momentum quickly. So usually this means you have flow and you have a fast closing valve. When that valve closes, all of that water that's been flowing, it has momentum, it has energy. That energy has to go somewhere, and what it goes into is a pressure wave that bounces around the system until it manages to dissipate all that energy. This can wreak havoc on a backflow preventer in a number of ways. It can cause everything from nuisance spitting, from those pressure surges, or even potentially destroy components within the valve. So let's answer a question I'm sure you all are here to learn, which is how much water can come out of that relief valve. So it depends on a number of factors. As we've discussed, the failure mode matters quite a bit. Basically, if the first check is fouled, how open is that debris holding that check? So how big is the debris that's fouled that check? Valve size, valve make and model matter, as well as the pressure the zone is being exposed to. So here we see a relief valve discharge graph. This is published by a major backflow preventer manufacturer. This is for a 2.5-inch RPZ, sort of a mid-sized valve. So keep in mind that several sizes might share one graph, as they often share the same relief valve. So you read the pressure in the zone is typically presumed to be inlet pressure, although it could be higher as a result of back pressure in a fouled second check. Let's go with something reasonable like 75 psi. Then you read the corresponding rate of flow on the y-axis. Here we get about 320 gallons a minute, which is very significant. So for a reference, if you had a 16-foot square room, so 16 by 16 with a 10-foot ceiling, it would fill that room full of water in 1 hour. One thing to note is this is absolute worst case discharge. This graph is created by installing the backflow preventer backwards and removing the second check and then running water through it. But it shows how dramatic the flow rate can be. 320 gallons per minute actually exceeds the rated flow of a 2.5-inch backflow preventer. So this is going into closer to what we'd call fire flow or UL rated flow. This is a lot of water. So now hopefully we know a little bit more about how an RPZ type backflow preventer works. We know how much water can come out of that relief valve. Let's talk a little bit about troubleshooting. So, you have a backflow preventer, you have water coming out of the relief valve. Let's presume it's not an emergency, right? So this is nuisance spitting, a little bit of discharge, small stream, something like that. So, what do you do? Number one, well, I'm going to be using this kind of right-hand side here. So common issue, relief valve steadily discharging. What do we do? First of all, if the discharge is occasional or random, it's probably fluctuating line pressure. A lot of backflow preventers get taken apart unnecessarily. You're going to give your customer a bill for essentially no reason, and they're not going to be happy about that just because they're discharging due to fluctuating line pressure. So if it spits and then 30 seconds later it spits again, and then 2 minutes later it spits again. It's not timable, it's not consistent. That's probably something external to the valve. But let's say you have regular discharge, either a continuous stream or a continuous drip. Here are those useful steps that you can go through to determine what's wrong. So the first one is shut down the outlet shutoff, watch the relief valve. If the discharge stops, your number 2 check is faulty, right? This is because, what are we changing? We're removing the downstream portion of your piping system from the backflow preventer. The only way that could be raising the pressure in the zone is if you have back pressure and a fouled second check. So if discharge continues, you open the number 4 test cock. We're going to create some flow. In fact, we have to create more flow than is coming out of the relief valve. So this is because, like I said before, you have to create that additional pressure drop across the first check by flowing more water, right? The more flow, the more pressure drop. In fact, you have to get it so that that check would essentially be open on its own if it weren't for that rock or piece of debris holding it open. So open that number 4 test cock. You got to create more flow than is coming out of the relief valve. And if discharge stops, that number 1 check is faulty. So we know this because once we created some flow and we lifted that first check up by itself, the relief valve seated because it's seeing that pressure differential, so we know the relief valve is good. So you go through all of this, you shut down the outlet shutoff, you open the number 4 test cock, you create more flow than the relief valve is discharging and nothing is helping, it is probably the relief valve itself. So relief valves do get fouled just like first and second checks. Again, that first check getting fouled is by far the most common failure mode, but it does happen. Also, I want to say pay attention to freeze damage. This is especially common in southern states where backflow preventers are installed outside, and especially with the kind of weather that we've been having the past couple of years, often in places that rarely or never get freeze. You might get below freezing temperature for multiple days. That breaks a lot of backflow preventers. Insulated enclosures can help solve this issue. So, we learned what causes RPZ discharge, how to do some basic troubleshooting. Now, how do we actually prevent it? First thing I'll say is that there's nothing you can do to 100% guarantee that an RPZ backflow preventer will not discharge out the relief valve. But there are things you can do that will really help and definitely help it from being a catastrophic situation. First one is flush the line before installation. This is particularly for new construction. Construction tends to stir up debris that's been sitting in the water mains, and also all of that new underground piping that's going in isn't necessarily clean and clear of debris when it gets installed. I've seen gloves, chunks of concrete, bits of 2x4s, animals, like just about everything that was probably not sitting in the water main. It probably came from that new underground pipe. For this reason, backflow preventers often fail their very first test after install, where they get installed, you turn the water on, and they start dripping. Then no one is happy when the contractor removes it thinking it's defective, only to have the return rejected because the manufacturer didn't put that rock in the first check. I can tell you we definitely do not ship backflow preventers out with big chunks of concrete holding the first check open. So it's very, very important to flush that line until the water runs clear. If the line was not flushed and the backflow preventer is already installed, a lot of manufacturers have recommendations on how to flush that line without removing the valve from service. Commonly, it's something like taking the cover off and removing the first check, and then opening that inlet valve to flush the line through there. You have to have some way to deal with all that water coming out, but at least you can do something to try and get any large debris out. You should check with the manufacturer or the valve's installation and repair manual to figure out if this is an acceptable thing to do. The second big thing you can do to avoid RPZ discharge is install a strainer. So let's talk about strainers. Strainers have some great advantages, but you should also know about some of the potential disadvantages. The big pro is, you guessed it, reduced chance of significant RPZ discharge. Now, a grain of sand can foul a check, so it won't necessarily prevent all leaks, but it should catch the big stuff. And remember, the larger the debris, the larger the leak. So if you can catch the big stuff, that's going to really help out from preventing those catastrophic discharges. Also, it will protect other downstream components. The backflow is not the only piece of equipment that can foul. So a strainer is going to help you protect everything else downstream, from pressure reducing valves to automatic control valves. The main disadvantage of a strainer, of course, is head loss. Pushing water through a screen is going to cause a pressure drop across the strainer, which has to be taken into account, especially in areas where your supply pressure is already low. The other disadvantage is it requires periodic servicing. So as the strainer collects debris, it begins to clog up, and that pressure drop across the valve will increase. This means that someone needs to be periodically checking the head loss, otherwise it won't be noticed until you're having issues with low pressure. So if you want to install a strainer, what are some best practices? First of all, you need to choose how fine or coarse of a strainer you want. The coarser it is, the better the flow rate through the strainer will be, and the more slowly it will clog. So this is going to increase your service intervals. You can wait longer before you have to go and clean it out. The finer it is, the more debris it catches, which is a good thing. It's going to better protect your equipment, but it will require more frequent servicing, and it will have a higher pressure drop. Most manufacturers have a standard screen size based on the pipe diameter, which is a great place to start if you're not sure if you want 1/32 openings or 1/16 inch openings, right? Second, it is best practice to install pressure gauges immediately upstream and downstream of the strainer. This is going to help you to assess clogging. Now, the pressure drop does correspond to flow rate. So if you don't have a measure of flow, it can be difficult to tell exactly how clogged the strainer is, right? When you compare, your pressure drop when you check it one day to pressure drop when you check it the next day, you're not necessarily comparing apples to oranges. But by monitoring frequently and recording those pressure drops, you should be able to get a trend to tell you when it's getting ready to service. It also needs to be installed correctly. First, this means installing it before the backflow preventer. I know this seems obvious, but I've seen people say, hey, you recommended a strainer? I got a strainer and it's downstream of the backflow. A strainer only protects the equipment downstream of the strainer. The other consideration is how you install it. It should be installed in a horizontal position or vertical down. It's relatively common to have them installed vertical up, but this means when you go to service that strainer, because it's clogged, any large debris are going to fall back down the piping, and it's just going to clog it immediately when you start it back up with a nice clean strainer that you've spent effort cleaning. So please, horizontal or vertical down only. I'd also like to note with that a Y strainer, such as this one on the screen, it needs to be installed with the drop leg, this portion sticking out, pointing down. Again, this puts gravity on your side, so when you go to clean it out, the debris has fallen down by the access cover, so it won't fall back into the system and just foul it up again. This strainer also has a plug on the cover where a ball valve can be installed to help flush debris out of the strainer. So you're getting that higher pressure differential, you can just open the ball valve, and that's going to take out some of the debris. It's a great way to quickly clean the strainer without shutting off water, but eventually these do typically need to be taken apart and properly cleaned. Now, there are many more considerations, such as material, strainer type, but beyond the scope of the presentation. We just want you to use a strainer. We have a great ebook coming out soon on this topic, so take a look out for that. Also, I do want to point out that you should check with your water authority. They're not always allowed, as the water authority sometimes wants the backflow preventer to be the first thing after the meter, and they typically aren't allowed on fire systems. Couple other common accessories. We talked about strainers, but expansion tanks and relief valves are also things you want to include. These are used to deal with thermal expansion. When you add a backflow preventer, you're creating a closed loop, right? You're isolating your system from all of the piping before that, whether it's in the rest of your building or whether it's in the larger water distribution system. That means if you have some thermal expansion, it doesn't have as much volume to go ahead and absorb that. So you can get dramatically increased pressures, which can start doing things like breaking second checks, which will cause some significant discharge. Also, it's expensive to repair. So if you're going to have a closed loop, a relatively short run of piping, it's in some sort of situation where you're going to get that thermal expansion, please consider an expansion tank or relief valve. The other thing is soft-seated checks. We talked about how fluctuating supply pressure can create some spitting from that backflow preventer. This can be solved with a soft-seated check valve, which is basically going to protect that backflow preventer from all those fluctuations. So we discussed why RPZ backflow preventers discharge, a little bit of troubleshooting, how to prevent it in the first place by using a strainer or making sure that you're going to deal with thermal expansion. But what about dealing with that discharge when it's happening? Well, there are two main technologies available. One is quite old, it's a drain, and the other is relatively new, flood protection devices. So let's touch briefly on drains. I'm guessing you guys know how drains work. So drain selection can be a whole other long process on its own. But the main issue when selecting a drain for a mechanical room with an RPZ backflow preventer is undersizing. So here we have that same 2.5-inch RPZ relief valve discharge flow chart. That 320 gallons per minute will require something like a 4-inch drain. This means that the actual piping to the sewer is 4 inches, not just a 4-inch drain piped down to a 2-inch or 1-inch line. I very rarely see a drain in a mechanical room with an RPZ backflow preventer that is capable of handling full catastrophic discharge. So, in fact, there are some places, some municipalities such as New York City, which require their design engineers to take a full 8 hours of RPZ discharge into account when they design that mechanical room. So not only do they have drains, they often supplement them with one or more sump pumps. For a large, 8-inch, 10-inch RPZ, it can be multiple large sump pumps. So that's what's actually required to deal with the potential of unmitigated catastrophic discharge. So if you have high water pressure and a large backflow preventer, it's going to be really costly to put in a 4-inch drain, especially say if it's on the 30th floor of a building. So what can you do other than huge drainage systems and big sump pumps to help deal with that catastrophic discharge? What are the other tools at our disposal? So the main one, I'm very excited to talk about these because they're pretty new to the market, are flood detection systems. These are available from a couple different manufacturers, and they're designed to help both detect and prevent flood conditions. So let's go through the parts of these systems: the backflow preventer, the detection, the shutdown, and the communication. So first we have the backflow preventer. So here it's in that red box. Hopefully you recognize it. The only additional thing I want to point out here is that air gap and drain line. It is a common misconception that that drain line is meant to handle all potential relief valve discharge. I think based on our previous conversation about what size drain piping would be required during a catastrophic discharge of an RPZ backflow preventer such as this one, that it's clear that that 2-inch drain line will not handle that catastrophic discharge. It's just there to route the much more common nuisance discharge, the drips, the little streams, to the drain. Also, you do need that air gap. Every backflow manufacturer supplies them as an accessory, and it's necessary to avoid making that discharge into its own cross connection, right? So you cannot pipe that discharge line directly into the relief valve without that air gap. So that's our backflow preventer. Let's talk about detection. So this is the first kind of new component in these detection and protection systems. This is what's going to tell you that something is wrong and that you have a potential flood on your hands. There's a couple different ways this can be accomplished. The first way is the way this system on the screen is set up. It's a wet switch that's down here on the bottom right. You can see it's on that T on the discharge line. So this can be somewhat customized, right? This works off of, in this case, 2 probes. It's just looking for contact. If you place those probes higher up in the discharge line, it's going to create, you're going to need more flow to set off the system. A little lower, you're going to need less flow to set off the system. This is nice because it can kind of be played with and customized depending on exactly how much discharge you can handle in your situation. The other nice thing about this kind of system is that it can be retrofitted to any backflow preventer. You don't need any special attachments. It'll work on anything. All you need is that discharge line. The other main way to detect an open relief valve is an actual relief valve position indicator. So this is a sensor embedded in the relief valve that detects when it is open far enough, and this is provided by some manufacturers. So for that type, you need that exact relief valve, so it's not necessarily retrofittable. The other big thing for both methodologies is timing. Once the switch is engaged, it needs to stay open for a set amount of time that you can control before the system takes any more action. This is to avoid any action in the case of intermittent or minimal discharge, or the fact that if you have your RPZ in a mechanical room in the basement, maybe an inch of water on the floor is no big deal. You don't want to hear about it until it's going to get pretty bad. But if it's, say, handling an air handler up on the 28th floor of your building, any discharge, that's going to potentially create a lot of issues, right? It's right above the penthouse suite. There you want some minimal discharge to give you an alert so you know you can go take care of that problem before it becomes a very expensive one. The next component is the shutdown. This can be optional, as automatic shutdown is not appropriate for every application. Fire sprinklers being the obvious one that comes to mind. You're definitely not putting an automatic shutdown on a fire sprinkler system. So this is going to use an electric signal to close a shutdown ACV in the event the system is triggered, based on all of that timing and positioning that we talked about earlier. Because the main failure mode is debris in the first check, this should stop the relief valve discharge. If the problem is the second check being fouled along with either back pressure or a fouled relief valve, you can still get that discharge, but those failure modes are much more rare. One thing to keep in mind is that once the system is triggered, it must be manually turned back on by opening a ball valve on the ACV once the situation has been resolved. So just keep in mind, not appropriate to every application, right? If your water gets turned off, just be mindful of what are all those repercussions. And finally, the last and maybe perhaps most important aspect of these new systems is communication. Someone needs to know that either your building is flooding or the water is shut off. This communication can come in a couple of ways. So one great way is communication with the BMS. This is great because it can integrate with an existing BMS software that has its own alerts, right? You're going to concentrate all of that into one area. The other kind is independent wireless alerts. This is also something that's really excellent, especially for situations where building maintenance personnel are not necessarily on the premises 24 hours a day. For some reason, these catastrophic discharges tend to happen at midnight on a Sunday. So you want some way when no one is in the building, except for maybe a security guard, to know that something is happening and either your water is shut off, you need to get someone in there first thing in the morning, or your building's going to start to flood and someone's got to get there. A lot of times when these things happen, it's not necessarily going to be catastrophic, but it will be if it's sitting there for hours upon hours before somebody notices, right? You don't want the first time your building owner to know that that relief valve is discharging when someone on the first floor's carpet is squishy, right? So the other thing to consider is how that signal is generated. The current systems on the market use a cellular signal, and that is for good reason. Building owners tend not to like having too much equipment on their Wi-Fi for security reasons. The only downside of this is that you have to have cellular signal at the wireless nodes, that's the place where your alert is coming from, to work, which you don't always have in a mechanical room, right? You're down in a basement, you're surrounded by steel and concrete. However, you can increase the wire length to try and locate a spot where you have enough signal. I know this particular unit on the screen, you get 100 feet of wire, up to 100 feet of wire, you can go find a place. So I'm very excited about these. These are the future of RPZ installations. They're the future of backflow. And the value of these should speak directly to the building owner because floods are extremely expensive. The average commercial flood claim is about $75,000. That being said, that can go easily into the millions. So if you're an engineer or you're a contractor, this is a great way to give some added value to your building owners. You can introduce them into something new. A lot of people don't understand about these RPZ backflow preventers. They don't know that they can discharge water. They don't know how much water it can discharge. It's exactly why we're doing this here today. Now you guys can take this information, you're armed with knowledge, you can go out and you can do a better job for, a good by your customers by having all this information on how to make sure their buildings don't get flooded and they don't come to you saying, why did you put this device with a, relief valve that'll potentially flood in, above my executive suite. So, in summary, after today, you should have a better understanding of backflow preventers, and you should be able to understand the basics of an RPZ backflow preventer, understand that basic root cause analysis and troubleshooting of an RPZ backflow preventer, how to determine worst case discharge, that's based on those published RPZ relief valve discharge rates that every backflow manufacturer should be able to provide you, understand the purpose and proper installation of a strainer with an RPZ backflow preventer, and finally, understand those new flood mitigation devices now on the market, along with how to size those drains. So, 2:51, we got 9 more minutes left, and with that, let's open this up to questions. I hope you guys enjoyed yourself.
Great. Thank you, Cam. We had several questions come through. First one's more of a housekeeping item. Would it be possible to get a copy of the slideshow?
That's a good question. I think this should be available.
We can send out the slideshow, yes. We'll get that to you. Next question that came through here. Does RPDA work the same way?
RPDAs do work the same way. So for those of you who don't know, we can zoom back a little bit in the presentation. RPDAs are basically RPZs with a bypass. Typically, they have another RPZ and a meter in the bypass. The only difference is, you might want to make sure that you're capturing the discharge both from the RPZ and the bypass and the main valve. So, but as far as the actual inner workings, it's exactly the same.
How can a 4-inch drain accommodate 320 GPM?
Yeah, I based that off of a drain calculator that I found. I will admit to not being a drain expert. I found some calculator online. So that's also based on an acceptable amount of head. I figure usually your mechanical rooms, they have a lip in there, built into the concrete that's a few inches high. That's going to give you some head pressure to help drain. But every situation is different. It depends on the length of the drain pipe before you hit the sewer, right? That's going to help you out. It depends on how many inches of water are acceptable before you start flooding something that's really going to affect it. So that's a calculation that really your building engineer has to help you out with.
Another question that came through, is this presentation available on the Watts website? Again, we could send it to you. You can do that shortly after the presentation ends, right at 3. Next question here, as a percent of BFP costs, how much additional cost is associated with the automatic shutoff system?
That's a great question that I don't initially have the answer for. I'll tell you, it's going to depend on the manufacturer. It's going to depend on the size of the valve, right? Because that shutoff ACV, right, it might not increase in price at the same rate as the price of your backflow preventer. I will say they are not inexpensive. That's something you're really going to want to go talk to your local manufacturer's representative and get a real quote on.
Do you have a diagram showing the placement of test cock number 4?
Do I have a diagram showing the placement of test cock number 4? And we can look at this backflow preventer right here. So there's your test cock 1, there's test cock 2, test cock 3, test cock 4. So basically it's going to be your furthest downstream test cock. It should be after the second check and before the second shutoff. So in this case, it's on the second shutoff, but it's right in front of the gate.
Need the open area of the drain strainer to determine the flow in the head above the drain prior to flow.
Yes, this is a good point. So I probably should have clarified. This statement over here, 300 gallons per minute equals a 4-inch drain. That is an estimate based on a specific circumstance that I plugged into a drainage calculator. Those are things available online. But in general, I would consult someone who's really specialized in this kind of stuff, a plumbing engineer, a master plumber, a manufacturer of drains, things like that, because it's going to depend on a whole number of variables exactly how large a drain you're going to need.
How much time between the catastrophic discharge and shutdown of the incoming water by the sensor and equipment?
So that's a great question. This is something that you can actually control. So in the case of this valve, right, so we have exactly how you're sensing, right? So here's your wet switch, kind of where those probes lay in the pipe. You have the timing, so how long do those probes need to be activated? So this works with all the different manufacturers. How long do we have to sense that relief valve is open, that there's water in the drain pipe before you activate? Because different people, different applications are going to be more or less sensitive. I know in this particular one, you could set it to a second, or you could set it to an hour. Maybe if it's outside somewhere and you just want to shut it off because it's going to be wasting water, you might set it for several minutes because maybe the situation will resolve itself. But like I said, if you're in a sensitive area, you have to squeeze a backflow preventer in some place where you're just not going to have adequate drainage with, more than a few gallons of water coming out is going to create a problem for you. You're going to want to make sure that the system is set up in such a way that it's going to activate quickly.
Do you recommend the stainless or the iron body backflow preventer? The iron body one is much heavier and more difficult to install.
That's a great question. they're all trade-offs. You know, I know obviously you guys all know I'm here at Watts. The stainless they're lighter, they're shorter, they're more compact. Some people like the epoxy-coated cast iron or ductile iron valves for different reasons. Sometimes it's, you know, familiarity, repairability. You know, you're looking at things like your head loss at a specific flow rate. All of those things come into play when you're deciding on what kind of backflow preventer you're going to get. I will say that stainless steel is certainly increasing every year, right? As a market, more stainless steel backflow preventers get sold and fewer cast iron backflow preventers get sold. So I think that stainless steel really is becoming the future. That's what most people choose to go with.
Okay, what is the best way to keep checking head loss?
What is the best way to keep checking head loss? So I think we're talking about a strainer. You know, if you have routine maintenance, you know, I see in a lot of buildings, maintenance personnel, they're going around, they might be reading, you know, doing sub-metering on different applications to keep track of that. They might, you know, they have to go check the state of various parts of the system. Just taking a look at the head loss across that strainer part of your routine maintenance, right? It doesn't have to be every day necessarily, right? It depends on how dirty your water is. But if just periodically, once a week, something like that, you're going down, you have gauges installed directly upstream and downstream of that strainer, just check your head loss, write it down somewhere, and once it starts creeping up, right, you should be able to kind of see a general trend. Go ahead and schedule some routine service.
Do you have any thoughts about strainers at every backflow device in the building versus maybe just at device for the building?
Right. So this is, do I want one big strainer right in front of the main backflow, or do I want one in front of every single one? I would love to see one in front of every single backflow. I know that's not always possible given, right, time restraints, or, well, space restraints, money restraints, right? You know, strainers aren't free. But I will say, you know, you have one big one on the backflow, that's going to have relatively large openings, right? Because you're going to want a fair amount of flow coming through that backflow preventer because it's servicing your entire building. Your smaller backflow preventers, whatever strainer you get with it is going to have smaller openings, right? So it's going to kind of increase those levels of protection. So I'd love to see a strainer in front of every backflow personally.
Are the shutdown valves FM approved?
UL and FM approved. I want to say, I know the one that you're seeing on your screen right now is not. I would say typically, so for those of you who may don't deal with fire, FM is typically a fire certification. Because I would never personally put a shutdown valve in fire service, I guess I don't necessarily see the need for FM approval. But to answer the question is right now that shutdown valve is not FM approved.
Okay, where in the line should a soft-seated check valve be located, up or down flow from RPZ?
I'm going to say typically it is going to be upstream of the RPZ because fluctuating downstream pressure, usually, unless it's fluctuating high, right? Unless you're getting back pressure and you have a fouled second check, that's not going to cause spitting. It's really the fluctuating supply pressure that's going to cause spitting. So you're going to want that soft-seated check valve on the supply side. The only caveat to that is if your problem is something like water hammer. So water hammer can cause spitting even if it's downstream of the check valve because basically that pressure wave is going to hit the downstream side of that second check, and that pressure can actually migrate through that second check by pressing it further into the seat. So if you're having some trouble, you know, and you can't figure out what it is, and you think it might be something downstream like water hammer, a soft-seated check valve can take care of that, or you can do the thing that is built for it, put in a water hammer arrestor. It's not something I touched on, but it's certainly the appropriate solution to water hammer.
With the sensors and interface, what suggested annual maintenance be required for the items?
Those sensors and interface, as far as I know, right, are reasonably robust. It wouldn't be a bad idea to just go ahead and during an appropriate time trip that sensor, right? You can do it by just pouring a bunch of water, right? Hooking up a hose, pouring a bunch of water down that discharge line, at least for the kind that you see it here up on the screen. I'm not exactly sure how you do it for the kind that's built into the relief valve, other than by forcing the relief valve to open. By doing something like bridging between two test cocks, that's really creating a cross connection itself. So I'd be very careful with that. Yeah, I would say it's a good idea. It's just maybe annually pour some water down that discharge line, observe it. If you have the shutdown valve, make sure you're doing it at a time where if you shut down the water for a few minutes, not going to be a big deal. So observe it, make sure you're getting the alerts, make sure everybody knows they're going to get the alerts and to ignore it. Let it trip, get the system back up and running, and just give yourself a nice little run through to make sure everything's hunky-dory.
Can an actuator be added to the suction side isolation valve of the backflow preventer to close when water is detected to save space in the mechanical room?
I need you to say that again.
I'll slow down. Can an actuator be added to the suction side isolation valve of the backflow preventer to close when water is detected to save space in the mechanical room?
Oh, okay. So you do something like putting an actuator on. In this case, right here, that suction side NRS gate valve. I mean, theoretically, sure. It's not how they come right now, so you kind of have to jury rig your own thing, and I would not recommend that because in general, messing with any part of a backflow preventer that's not manufacturer approved is not a good idea, right? So, either you're going to get fail of backflow test because there's going to be some stuff on the backflow preventer no one knows about and isn't manufacturer approved, or worst case scenario, something goes wrong. These are safety devices, right? So that's exactly, they're in there because they're protecting our water safety. So typically your inspectors take messing with them very seriously. It's a good idea though. I will certainly pass that along.
Is the flood detection protection system exclusive to Watts?
Good question. No. So there's another manufacturer that has it. I will say they're different, right? Because this is an ASPE course, right? It's not really, for me to try and sell you guys things. I'm not going to go into too much detail, but you should have my email. You should have my contact. Drop me a line. I would be happy to discuss it further with you.
Great. We are looking for a discharge ref for an LF909 2-inch, which is not in the install manual. Where can I get this info?
All right. I will email that to you. So I think Greg's taking a...
Yeah, I'll note that down for you.
Yeah, I'll make sure you get that. Then I'll make sure it goes in the installation manual.
Okay, I think we have one more question here. Which model RPZs have relief valve position indication for use with automatic water shutoff?
Sure. I can tell you that it's not Watts. The other big manufacturer, right? That's how they've chosen to do it. If you want to talk again, if you really want to talk about comparisons, I'd be happy to do that offline because I don't want to get too much into the commercial stuff since this is for, ASPE. But Watts uses this system that you see on screen that has that the wet switch in the discharge line.
Okay, and is there a straight pipe length requirement upstream or downstream of the RPZ before a bend can be introduced into the piping?
That's a great question. I know that there is a recommendation that rarely gets followed. And, you know, you'll probably notice a lot of times we sell what we call N and Z type backflow preventers, where we actually build in elbows right at the discharge and the suction. So I won't worry too much about it, but that being said, having straight lengths of piping is great because it makes it, the backflow preventer, just operate a little easier because you're going to introduce less chaotic flow to the suction and discharge side. I'm going to have to look up to see if we have specific recommendations, but like I said, because we do have those N and Z type backflow preventers, it's not a huge consideration the way it might be for, say, a pump.
Okay, and are manufacturers' air gaps interchangeable, or should they be paired with like parts?
Usually they're not interchangeable. So on purpose, most of these, it's not like an NPT fitting, and it's not an NPT fitting because manufacturers want to make it very difficult for people to block that relief valve, right? So if all it was a, you know, say a 2-inch NPT, and somebody who's maybe not well acquainted with backflow preventers sees it leaking, they're going to find a way to plug it. So for that reason, they all are a little different. It's nothing standard. You have to typically pair the recommended air gap with that backflow. And also, those air gaps carry their own approval. So there's actually an ASSE test for those air gaps, and it's that air gap with its intended backflow preventer. So yes, please do use the manufacturer's recommended air gap.
Great. Those are all the questions we have. Cam, any closing remarks?
Nope. Hey, thank you guys so much for attending. I really appreciate it. Like I said, if you have any further questions, feel free to drop me a line. My email and phone number, I believe, were part of the invitation. Yeah, and get out there and help us protect our water and help protect your customers from the potential of flooding from these RPZ backflow preventers.
Okay, great. Thank you, Cameron, and everyone who joined us today. Just to let you know, a recording of this presentation and your CEU credit will be emailed to you within the next week or so. And again, if you have any more questions, please don't hesitate to reach out to us. Thanks again, and have a good day.